In this video, we are going to look at vector-valued functions and space curves. So a vector-valued function in the unit vector form is going to be r of t is equal to f of t. So it's being a function in terms of t, I, and g, so a function in terms of t, j. Or if we're in 3 space, we would also have h of t, k. And if we're in component form, we can write it in the component form where we have our brackets showing that it's a vector, and we have f of t and g of t in 2 space, and f of t, g of t, and h of t in 3 space. Now, our parameter can be between 2 real numbers, say a and b, or it could take on any real numbers. The component functions themselves may have domain restrictions that will restrict the values of t. We usually use t as our parameter because it usually is in respect to time, but not always. So t is by default. You could use something else, we typically don't. So let's take a look at our first example here where we're asked to just evaluate or find the following values at r at pi over 4, r of pi, and r of pi over 2. Basically, what they're asking us to do is just put in to each component that value. So I'm asked to do 3 times the secant, and I wrote sine because I like sine, the secant of pi over 4, that'd be I, plus 2, the tangent of pi over 4, j. This then becomes, I'm going to get my unit circle out, and the secant of pi over 4 is going to be the square root of 2 over 2. So this is going to be 3, and the secant of pi over 4 is going to be the square root of 2. It'd be 1 over the square root. It'd be square root of 2. So it's just square root of 2. I, and then it's going to be plus 2. The tangent of pi over 4 is 1, so then it'd just be j. And so that is my final answer. Now let's take a look at pi. So we'll do 3 the secant of pi I plus 2 the tangent of pi j. Now the secant is the reciprocal of cosine, so that's going to be 3 times, excuse me, negative 1i, and then plus 2 times the tangent of pi is 0, j. So I end up with just negative 3i. And of course, I can put on 0j if I'm inclined, but not necessarily needed. Taking a look at our next one, I'm going to put it down here because it's kind of squished. So I'm going to put in pi over 2. So I have 3 times the secant of pi over 2, I, plus 2, the tangent of pi over 2j. But wait a minute. The tangent of pi over 2 is undefined. So I can't do the tangent of pi over 2, and the secant is a reciprocal of cosine. So the secant of pi over 2 is also undefined. So that's where it loops back to this, which is if it's restricted on each one of those functions of t, then that value of t would also be restricted, and that leads us into thinking about domains of these. So when we're looking at the domains, well, I will talk about the domains in a minute. So when we're graphing a vector-valued function, the graph, if we only have I and j, the graph would be of the form t, r of t, where what we'd be graphing is the t being the input and r of t being the output of this. And the path that it traces the plane curve. A graph of the vector value function where I have f of ti, g of tj, and h of tk consists of all of the set t, r of t, and the path that it traces is called the space curve. Any representation of the plane curve or space curve using the vector value function is a vector parameterization of the curve. So first, let's talk about what the parametric equations of this would be. Here's our vector valued function. The parametric equations of this would be x of t is equal to this part, 3 minus t. Y of t would equal this part, -1 minus t, and z of t will equal this part, which is 4 minus 3t. So it is that simple. So here are some important takeaways when working with parametric curves. Any curve has an infinite number of reparameterizations. For example, we can place t with 2t in some of the curves without changing any shape of the curve. The interval in which t is defined may change, but that's about it. Given a vector value function, we can define x is equal to f of t and y is equal to g of t. If the restriction on the values of t for each one of those individual functions is some value in this interval, then the restriction has to be enforced on the parameter. And the graph of the parameterized function has to agree with the graph of the vector value function, except that the vector valued graph would represent vectors rather than points. And since the parameterization of a curve defined by the function y is equal to f of x is also a possible representation of arbitrary plane curved by a vector valued function. So now we're back to talking about the domains. So now we had like a little interlude, let's talk about the domains. When we write the domains of these, it's going to be slightly different in the way that you're going to see the domain wrote. You're going to see it maybe wrote as the domain, and then I'm going to tell you about what I'm looking at. In this case, I'm looking at r of t. And then this is going to be equal to, and we're going to usually use set builder notation and not interval notation. So I have to define my variable, so it's t. And now let's talk about t. Well, this part doesn't have any restrictions. This one does. We know the square root of t minus 3. We have to ensure that the t minus 3 is greater than or equal to 0. That has to hold true, or otherwise we're in the land of complex, and we'd prefer not to be there. So we get t is greater than or equal to 3. So that's the first part. We also have this one. This is that we know that the denominator can't be equal to 0. So t can't be equal, t cannot equal -1/2. Because if t equals -1/2, then we have a problem. However, this is going to dominate this. That t obviously greater than 3 is going to dominate the fact that t cannot equal -1/2. And so my domain is such that t is greater than or equal to 3 and t is any real number. Let's take a look at our next example. I'm going to look at it each component. First, this component. There's no restrictions on e raised to the -t, so we're cool there. There's no restrictions on that one. We're cool there. Here's where we have a restriction. We know that the natural log of a is perfectly great and wonderful so long as a is greater than 0. So we know that t minus 1 has to be greater than 0, strictly greater than 0, so t has to be strictly greater than 1. So my domain of r of t is t such that t is greater than 1. T is greater than 1, and t is any real number. If we're asked to sketch the curve, we want to think about where we're going to have asymptotes. So we know that when we have an asymptote here, we have pi over 2. We knew that from before. Pi over 2 has a vertical asymptote, or has an asymptote. So we know that this one is undefined. We also know that 3 pi over 2 is undefined. So we know in those places our graph is undefined. So let's see what that equates to here. So let's do some curve sketching by choosing some values. I chose from t equals 0 to 2 pi. So I'm going to put in t equals 0. So I have 3 times the secant of 0 plus 2 the tangent of 0. And this is ij. Now, what I know is that the secant of 0 is 0, and the tangent of 0 is 0, so I end up at 0. So right here, I am at 0. Now I'm going to do the pi over 4, so I have 3, the secant of pi over 4, plus 2, the tangent of pi over 4, and this is j, and this is I. And we end up with what we had before. I'm just going to erase part of this so I can get, I'm going to just do the answers. You'll understand that I'm putting in 0 and I'm putting in pi over 4. When I put in 0, I'm going to get the 0 vector out. That's this. When I put in pi over 4, I'm going to get 3 the square root of 2i, and then it's going to be plus 2i, or excuse me, 2j. So I'm going to go 3 the square root of 2 in the I direction and 2 in the j direction. So we have this point right there. And then we're going to look at 3 pi over 4. So secant is negative in that quadrant. So we're quadrant number 2. Secant is negative. So this will be negative 3 square root of 2. And then tangent, 3 pi over 4 is also negative. So it'd be minus 2j. And so it's going to look something like down here. Let's see if we can put in 5 pi over 4. We put in 5 pi over 4, and we're in quadrant number 3, 4. We're in quadrant number 3. So secant is positive or negative, so it'd be 3 the square root, negative 3 the square root of 2i. And then tangent will be positive, so 2 in the j direction. So we have something that looks like, let me see, negative, and then here. And then 7 pi over 4 is going to be a positive 3 the square root of 2i. And then tangent will be negative, so minus 2j. So it's going to look like something like there. Now, we don't have a really good idea of what this looks like. So I would probably choose some points that are between 0 and pi over 4 to kind of fill in this. And then I might choose like pi over 6 maybe to see what's happening as we go further out. The gist of it is that your graph is going to look something like this. It's going to come down to about 1, and it's going to kind of look like this. Now what I would suggest you do is, and this will go to negative 1, is get some other points in here. I actually didn't choose enough points to get an idea, a really good idea of what the shape is. So I would choose maybe like pi over 12 and maybe 11 pi over 12 and go from there, because you're not going to really get a really good idea of what the graph looks like with the points that I chose. And we have these asymptotes. These asymptotes are a representation of when we reach pi over 2 and when we reach 3 pi over 2. So that's where my vertical asymptotes were, because they were undefined. That's when you go to graph it, you're going to find the asymptotes. That's what they're going to look like. Instead of being up and down, they're kind of diagonal. If we're asked to find a parametric equation for the shadow of the cylinder on the XZ plane, what I'm going to do is I'm going to go back to what we learned in section 1.1. If we have to parameterize a conic that is a ellipse or a circle, remember that we had from section 1.1, if we have the conic, which is x minus h, the quantity squared, over a squared, plus y minus k, the quantity squared, over b squared, is equal to 1. Then we can parameterize it where x is equal to, oh, that reminds me. I do need to put in my direction, and my direction is actually going in this direction. And then this one, as we were filling this out, we discovered when we went from 3 pi over 4, so this is also going in this direction. Don't forget, when you parameterize your graphs, you do need to show directionality. Okay, back to this. Easily distracted. Here I am. What we had from section 1.1 would x can be replaced with the parameter of h plus a, the cosine of t, and y is equal to k plus b, the sine of t. And you're thinking, but wait a minute, I don't have y. Well, okay, make this z. So let's make this z. It still works out. What I end up with is x of t is going to be equal to. Now, what I'd have to do to put this in the right form is have to divide every term by 9, and so I'd have, and that should be squared, I should have a squared, which is 9, and so a is 3. So this is going to be 3 the cosine of t, and my z of t is going to be 3 the sine of t. And the reason I can do that is because they're saying for the shadow of the cylinder in the xz plane, so that gives me these parameters for x and z, but it says, wait a minute, what happened to y of t? Because of the fact that we are on the xz plane, y has to be 0. And so the parametric equations in this form would be 3 the cosine, not cosine of t, 0, and 3 the sine of t. All right, so find a vector value equation, boom, for the cylinder. Oh, we know what that looks like, and the plane. Oh, okay. Well, we know what x of t is, and so we're looking for the intersection of these. I shouldn't say in there somewhere, the intersection. Find a vector equation for the intersection of the intersection. There we go. X of t is still going to be the same thing. So that's going to be 3 the cosine of t. And z of t is still going to be the same thing. That is going to be 3 the sine of t. Now the only thing we have to do is we take this equation right here, replace x with 3 cosine of t, z with 3 sine of t, and solve for y. So y is going to be equal to this one that was still there, minus 6 times my 3 cosine of t, because I've replaced this x with 3 cosine, and I moved it to the other side of the equal sign. And then it's going to be minus 7, and then it's going to be 3 the sine of t, because I moved it to the other side, and I replaced z with 3 sine of t. And it's all going to be divided by 2, because that is the coefficient on my y. So my answer now is 3 the cosine of t, 1 minus, let's go ahead and do that multiplication. 18 the cosine of t, minus 7, let's do that multiplication. 21 the sine of t, divided by 2, comma, and then my last one is 3 the sine of t. So find a vector value function for the equation of these two when they intersect. I don't know why I didn't want it for the intersection. Find a vector parametric equation for the intersection. For the intersection of these two paraboloids, not graboids. Anyways, so the way that we're going to approach this one is, because y is equal to y all day long, let's set these equal and see what happens that shakes out. So we have 7x squared plus 6z squared is equal to 13 minus 6x squared minus 7z squared. So this looks like it might be a pretty nice conic. Let's go ahead and bring the x's and z's to the other side. And I get 13x squared plus 13z squared is equal to 13. I divide everything by 13 and I get x squared plus z squared is equal to 1, and this is nice. So x of t is going to be equal to 3, not 3, 3 is up above. This time my a value is 1, so it's just going to be the cosine of t. My z of t is just going to be the sine of t. That's kind of nice. So then the last thing we have to do is find an equation for y. Let's use this one. Y of t is going to be equal to 7. I replace x with the cosine of t, the quantity squared, plus 6, the sine of t, the quantity squared. And so what I'm going to get is the cosine of t, comma, 7, the cosine squared of t, plus 6, the sine squared of t, and then I have the sine of t. And that's it. That's my answer. Not bad. Let's talk about limits and continuity. So a vector-valued function r has a limit L as t approaches a. It can be written in this form, provided, of course, that as t approaches a, that the vector value function minus L is equal to 0. Cool. In practice, this is what we do, is that we're allowed to take the limit of each one individually. Notice that I have, as t approaches a of r of t, it is the limit of the first component, the limit of the second component, that's still t approaches a, it's f of t and g of t, and of course we can go all the way out to 3 components, the I, j, k components, and provided, of course, each and every one of those limits exists. So if I'm asked to find the limit as t approaches 4, I ask myself, is that going to be defined on each one of these? And the answer is no, it is not defined on this one because of the fact that the domain is restricted to 4 there. So because of that, I can't do that with a direct substitution. So let's see if I can do some algebra on that middle term to allow myself to do a direct substitution. One of the things that we learned way back when is a squared minus b squared can be factored into a minus b and a plus b. What happens when I have, say, x minus 5? Can that be factored in the same manner? And you're going to say, absolutely. It's going to be the square root of x minus the square root of 5 multiplied by the square root of x plus the square root of 5. Cool. That means I can take this piece, which I can't do a direct substitution on, and do a little bit of algebra. This goes way back to Calc 1 when we learned that if we can't do a direct substitution, does that mean we're done? Not necessarily. So I'm going to rewrite this middle component as t minus 2 divided by the square root of t minus 2 and the square root of t plus 2. And I am using this. So now I can take and do a direct substitution because this will cancel with this, and this middle component really is 1 over the square root of t plus 2. So let's go ahead and take the limit now. The limit as t approaches 4 of the square root of t minus 3, that'll be my first component. And then I'm going to take the limit as t approaches 4 of 1 over the square root of t plus 2. And then my last one is the limit as t approaches 4 of the tangent of pi over t. So I can do a direct substitution, and when I put in t for here, I'm going to get 1. When I put in a t for 4, to replace t with 4, I'm going to get 2 plus 2, which is 1/4. And I put in 4 here. The tangent of pi over 4 is 1. And so that is the answer for that one. And that was A little bit of work, not too bad. Now, this one is like, what? It's slightly different. It's still the same. We're still going to do it component by component because r of t can be rewrote as e of t, the sine of t, and the natural log of t. Now, no problems here on this one when I do a direct substitution. So the limit as t approaches pi over 2 of r of t is going to be equal to the limit as t approaches pi over 2 of e to the t, the limit as t approaches pi over 2 of the sine of t, and then the limit as t approaches pi over 2 of the natural log of t. This then gives me e raised to the pi over 2, the sine of pi over 2, which we can do, so we'll put in 0 for that one. That's a nice number, so we'll put 0 in. And then, of course, the natural log of the pi over 2. And that's it. That's all we're learning so far in this section. That's all we learned in this section. Actually, not bad.